Come on. Okay, can you see that okay? No. Okay. So, we'll start now. We have talked recently about pressure, and we're going to talk about the relationship between pressure and volume and temperature and so on. So, if a gas is kept at a fixed temperature, then we have this relationship between pressure and volume. Turns out that pressure will be inversely proportional to volume. This actually is something I know some people know already. This is called, what law is this called? Someone might know this. Boyle's law. So for example, if you have a gas and it's at, let's say, 10 meters cubed, 300 Kelvin, and the pressure, I don't know, would say is 1 megapascal, or maybe that's a little too big, 1 kilopascal. And if you were to change this now to 5 meters cubed, keep it at 300 Kelvin, then what would happen to the pressure? Does it increase or decrease based off of this formula? Increase to what? 2 kilopascals. So if you half the pressure, the volume, then you would double the pressure, and vice versa. And this is Boyle's law. Is it always true? No. It's true when the temperature is constant, and it's true for most gases, but not all gases. So we just need to say it is true for what we call ideal gases. It is true for an ideal gas. This is basically Boyle's law. You get this sometimes in the exam as a short kind of 1-mark question. They would say something like, a tire has this volume, this temperature, this pressure, and the volume and temperature are now that, what is the pressure? You know, a real kind of quick 1-mark question. Okay, so that's handy for you in the exam. Okay, so if we go on now. Yeah, okay. Okay. Can I go down? Yes? Yeah. Okay. So there's another law which now relates volume and temperature. So what do you think happens when you heat something up to the volume? It increases, okay? So this next law says that volume is proportional to temperature, but in this situation is if the pressure is fixed, is constant, yeah. So again, let's take our gas, and we have our gas, and let's say again it's 10 meters cubed, it's 300 Kelvin, and and pressure, we say 1 kilopascal. Oh, by the way, we must use Kelvin for these formulas. I'll say that again. We must use Kelvin and not Celsius for our formulas. You have done Kelvin in chemistry at this point as well. Anyway, suppose now I change this to, I keep the volume, I don't know the volume, but let's say I half the temperature, and it's still 1 kilopascal. So then what would happen to the volume? It's half as well. Yep. Now this one also has a name. Yes, very good. Charles's law. So this is called Charles's law. Now what's interesting is these are only true for gases, but you can kind of picture it's true for, mostly true for solids. That if you heat the solids, the volume gets bigger, and if you cool the solids, the volume gets smaller. And same for liquids. If you heat the temperature of a liquid, it expands, and you cool it, contracts. There is one exception, an important exception to that. Does anyone know? Important situation when this rule isn't true, that volume doesn't increase with temperature. It's something to do with water, yes.
When at some point it behaves open.
Yeah, I'll draw it here for you. So here is volume, here is temperature, and here is 0 degrees, and here is, let's say, 4 degrees, 8 degrees, minus 4 degrees, and minus 8 degrees. So as the temperature gets smaller, the ice gets tighter, the volume gets smaller, so the graph goes like this. Then you increase the temperature, what happens to the volume? It increases. Yeah. And then what happens at this point? It turns into a liquid. But this is really strange now. The volume decreases. Yes, decreases between 0 and 4. And then it increases again back at 4.
Is it like anomalous under the water?
Yes, or the weirdness of water, if you want. So I'm kind of drawing that not so great. But here to here, this is when it's really strange. That the water actually, instead of continuing to increase, it gets smaller. And this is the reason why ice floats. Really, ice should not float, it should sink. If you have any other liquid, like liquid nitrogen, and you have liquid nitrogen as a solid and liquid nitrogen, nitrogen as a solid and nitrogen as a liquid, if you put the solid on top of the liquid for nitrogen, it doesn't float, it sinks. So this is weird with water, that between 0 and 4, instead of increasing its volume, it decreases, and then it goes back to increasing at 4 degrees. Okay, so this we'll talk about later today as well, but that is very strange. I don't think there's any other liquid that does this. I don't think so. And I don't think so, is there? No, I think it's only for water. Okay. Alright, so just make note of this graph. I'm not sure how, I'll have to get you a graph on Google later or something, but the key thing is here it's increasing, and then here it's decreasing, and then once it goes past 4 it goes back to increasing. Okay. Going on, so right, and there's one more formula, but I don't think it has a name. So what we've done so far is we've had a look at pressure and volume, volume and temperature, and then what else? possibility is left as well? Pressure and temperature, yeah. So what do you feel is the relationship here? If you increase temperature, what do you think happens to the pressure? No, increase. If you make something hotter, it's more heat, it's more pressure. You know, and then if it's too hot, it explodes. You think about a gas in a container. So this law here has no name, so we'll just call it no-name law. And its pressure is proportional to temperature. So again, with our gas, if you have like 10 meters cubed, 300 Kelvin, and 1 kilopascal.
So when the volume is constant.
Oh yeah, so like, yeah, the other thing is fixed always, volume is constant.
But then, if the volume is not constant, then...
Oh no, then that we'll deal with in a moment, yes, yeah.
Steven, isn't that called pressure law?
Oh yeah, but I don't just know the person's name after it. Yeah, I can just call this the pressure-temperature law. You know, I meant no name as in no person's name, like Boyle or Charles. Yeah, I'm not really going to call it the no-name law. I'll end up calling it the pressure-temperature law. Right, so then this here becomes, so we keep the volume the same. The pressure, we increase it. We increase the pressure to, let's say, 2 kilopascal. So then what will the temperature be here? It will be 600 Kelvin. Okay, can I go down? Yep. Alright. Now, I know you've done this in chemistry, but I'm going to say it anyways. Avogadro. So that's what we're going to look at next. Unless you all tell me not to do this part, that you're so confident with it.
No.
We can fast forward over this?
No,
No, really? Seriously, yeah? Alright, fine. Okay, so, one problem when we're talking about gases and atoms and anything is that we have a huge number of atoms, particles, and so on. So Avogadro's constant is kind of a way to handle the size of the numbers, and it has interpretations and so on. But for the moment, I'll just say Avogadro's constant is a number. I have it right here. 6.02 times 10 to the 25, and I'll just simplify things. And this is called a mole. A mole of things. And I'm deliberately using the word things here to say it can be anything. And I think the example Lorraine goes with is bins or something.
It's 25 or 33.
Oh, hang on. Oh yeah, sorry, 20, I wrote it down wrong. Sorry, thank you, 23. A mole of things is 1L of them. You know, so like 1 mole of, I don't know, students would be 6.02 times 10 to the 23 students. So that's the first thing. At the moment, there's nothing special or fancy about it. It's just a constant. Okay? And where exactly does this constant come from? Or what's the meaning of this exact number here? Well, the reason is... Oh, sorry, can I go down? Well, there's nothing particularly interesting there. We'd say that if we have 1 mole of C12, you know C12? You've done this in chemistry? Carbon 12. 1 mole of C12 has a mass of 12 grams. So this is actually the definition of a mole, or an Avogadro's amount of material. That if you have a mole of C12, it should have a mass of 12 grams. Yeah? And that's kind of convenient. Now, it's not exact, but roughly, if you have something like hydrogen, what's the atomic number for this? 1. So if you have 1 mole of hydrogen, it should be roughly 1 gram. Okay? And if you have, what's next? 1 mole of helium. No, 1 gram, I believe. Yes.
But then what is the connection?
What's the connection? Well, this here is just the definition, the formal definition. Here is Stephen's informal definition, and then this is the formal definition. A mole of C12 has a mass of 12 grams. So this is when you know you have a mole. That's how big a mole is. It's how many you need of C12 to make it have a mass of 12 grams. So that's why it's so big. But that's just, there's no relationship between that and what's next. This is just the formal definition of a mole. Formally. But what I'm saying is, what's also convenient about using this is that 1 mole of hydrogen is roughly 1 gram. 1 mole of helium is roughly 2 grams. Okay? What's next after this then? Oh, give me another atom where you know the number of it. The number of protons and neutrons.
Oxygen.
Yeah, oxygen. Okay, so oxygen. How many protons? 16. No, 16 protons, and how many neutrons? Oh, sorry, 8 and 8. Isn't oxygen 8 and 8? 8 protons or 16 protons? Is it? Yeah.
Yeah, it is.
Is it 16 protons in oxygen?
Yeah.
Or is it 8? Take out your periodic table. You have it, right?
No. 16 is the value.
Yeah, so how many protons in oxygen?
8, you're right, so yeah.
8 and 16.
Yeah.
Sorry, here, this one here was 1, 1, and here 2, 2. I know there's neutrons, but just for the moment I didn't put in any neutrons. So here, 1 mole of oxygen 16 is roughly 16 grams. Okay, so this is part of the convenience of moles as well, that it lets you, work out how many oxygens you have. If you know that you have 16 grams of it, then you know you have a mole of it. Okay, so this is just something useful with moles. Okay, right, next now. Well, okay, molar mass. I'm sure you know this as well. What's molar mass? Yeah?
Mass of the atom. Mass of the proton.
Molar mass? Molar mass is possibly mass of 1 mole, right? Makes sense? Molar mass, the mass of 1 mole. So for example, what would be the molar mass of students? Big or small?
Big.
Ginormously big, because it's going to be the mass of L students, which is what, 6.02 times 10 to the 23. So this is going to be something huge, like 6 times 10 to the 25 kilograms per mole. It's huge. What's the molar mass of hydrogen? Yeah, 1. Well, if you look back here, when I have, well, not 1, but 1 gram, because when I have 1 mole of hydrogen, I have 1 gram. And what's the molar mass of oxygen? 16. 16 grams, because 1 mole will be 16 grams. I'm a little bit worried that, anyway, has it been a while since you did this, or, okay,
Yeah.
it's fine, okay. Going down? Oh, sorry, do you have that? Yeah.
23.
What's, no. This is, I roughly said a student's 100 kilograms, just to, this is, no, this is now the molar mass. I'm saying for students to be some number like this, maybe not as big. I think students generally aren't 100 kilograms. Alright? Okay. Can I go down? Yes? Okay. So what's convenient is, those 3 laws I gave you at the start, you can put them together in one law called the ideal gas law. So this Boyle's, Charles, and the pressure volume one, you can put it all together in one law as pressure multiplied volume is proportional to, and this is where I needed to do the moles, the number of moles you have of the gas multiplies temperature. So this is the pressure, this is the volume, this is the temperature, and then this here is the number of moles of the gas. Yes, well, there's many ways to rewrite this, but for our physics exam they keep it like this normally. So if you want to get rid of the n here, which is just how many, much of your gas you have, it's like a mass, we just need to introduce a constant. So you have PV equals OR/T. And the OR, funny enough, is called the ideal gas law constant. Which is, yep. They didn't get enough credit for it.
What would they use a specific name for R?
Oh, the constant? I always see it in books as ideal gas law constant. Let me see. Boltzmann's constant now is related to it, but it's not exactly the same thing. I think Boltzmann's constant is the ideal gas law constant multiplied by Avogadro's number or something, but we'll do that in a moment. Anyway, the ideal gas law constant, what's the units for it? The units would be, let's see, pascals meter cubed per Kelvin mole, when I rearrange this. That's the units. And its value is, I think, about 8.31, isn't it? Yeah, 8.31. So it's 8.31, well, I just wrote the units there, but that's what the value for ore is. It's a constant, it's just a constant. Okay. So this is very important. Very important. Okay. Now, this is not really what I want to do today. This is what I really want to do in the next class. But I'm just trying to get us thinking a little bit about pressure, volume, temperature, and so on. So I will return to this, maybe in the next class, or maybe later today. But I need to do another formula, and this is the tricky one. Quite tricky. Okay. Can I scroll down? All right. So the reason I was talking about moles, pressure, and volume is because we can link them all together, and the reason why the n is here will become clear now. Because we can think about solid, liquids, and gases as just being atoms or molecules moving around. So we think of a gas, a liquid, or a solid just as all the little atoms moving around. And the difference between the three, solid, liquid, and gas, is the difference between how much each of them can move. So what do you think? For a gas, do we have lots of freedom? Yes. Gas, that means there's lots of freedom for the molecules to move around. But then if we have a solid, not so much freedom. They're more fixed into place, but they're still moving. So for a solid, it's roughly fixed, but with some movement, not much so. And then what about a liquid? That's more, it's not very fixed, but it's not very free. It is in between the two. So about half and half. This is some freedom. Yes, what's wrong?
No, it's a flow.
Huh? Never mind, okay.
Sure, doing this thing.
So what I'm saying is, we know from chemistry that everything is made up of atoms. And the only thing that makes a solid, a gas, or a liquid different is how free the atoms are to move. So a solid, the atoms are locked into place with some freedom to move. With a gas, the atoms are not locked and they're completely free. And a liquid is a mixture between the two. The atoms aren't locked, but they're not completely free, so there is some movement and some freedom. That's what makes the three states different only, is the freedom of the atoms to move. So what I'm going to look at now is the gas one here. Okay. Let's see if I can find this here. Right. Okay. Can I go down? Okay, so let's have a look at our gas here. Okay. Now, this proof is a little bit long. So what I'm doing is I'm picturing my gas in a box just to make it easier. Okay. Let's have a look at one particle as an example, and it goes along and then it hits the edge of the box and bounces back in a straight line to make it easy. What is the change in momentum for this atom? That's called the impulse. So the impulse is the change in the momentum of this one atom. And let's say before the collision its speed, well, we'll write the formula down, it's mv minus mu. And of course this m is very, very, very small. It doesn't have to be an atom, I just said an atom, but it could be like a molecule, like H2O. I just wrote atom. Okay. Yes? Okay. Oh, and I'll make the box, I'll say each side is L in length. Okay. Right, now, if we say the collision is perfectly elastic, the speed before the collision is v, and then after the collision is minus v. So then this will be mv minus mv, which is 2mv.
Could you repeat that?
Yes. If it's v before it hits the wall and bounces back perfectly, then it'll be minus v after the collision. So that's what I just did. I replaced, well, I have the signs the wrong way around, it doesn't matter. That the v and the u are the same, but the only difference is the signs. So, yeah, it doesn't matter. Okay, so that's that one. Right. Now, the time. How long does, we have our distance, speed, time here. Distance, speed, time. The time is the distance divided by the speed. Now, for this example here,
is that mv minus mv?
mv minus minus, yeah, so I'll just write in as plus. Yeah. Okay. Now we can't really know how far the molecule has travelled, right? Because we don't really know where it started and we don't really know where it ended. So we're not sure. Plus, I drew it going in a straight line, but maybe it was going from one corner to the other corner and bounced back. We don't know. But what we can say is the distance is, we'll say, roughly 2L for the journey. Now, I know sometimes it'll be less, sometimes it'll be more, whatever. That's not too important. It's not to worry about, okay? So if the distance is 2L, what's the time? Time is distance divided by speed. So it's the time. Oh, and the speed, of course, is constant. All right. Okay, what's the force? Do you remember that we said force is the rate of change of momentum divided by the time? When the particle hits the wall, that's a little force. So the change in momentum is 2mv, and the time is 2L over v. So the 2's cancel, and we get mv squared over L. Yes. Yes, that's right. Yeah, now the distance is 2L, yeah. But, yeah? That's this here. Now, like I said, we don't know what the distance is because, for example, maybe it went L and L, or maybe it went L over 2 and then L over 2, or maybe it went L, so it went from corner to corner, which would be something like root 2L, and back again, you know. So we don't know. So we just say, okay, we think it's roughly twice the length of the box, 2L. On average, roughly, just roughly, yeah?
I couldn't get clearly how you go minus mv minus mv.
How did I got 2mv?
Yeah.
Huh? Well, I said before inflation it's v, and then after inflation it's minus v. Now, I just wrote it backwards. I should really have minus 2mv, but I don't care about the sign, I just want the number right now. So before it's v and after it's minus v, so it'll be like a minus mv minus mv, so minus 2mv. So I should really have a minus, but I'm not worried about the sign right now. It's not important for what I want to do.
Are we ever going to be asked to prove?
No, you're not, but what they sometimes ask you to do in the exam is to explain something. And it's good if you see the proof for the result I get at the end. Okay, do we go on then? Yeah. Okay, so I have this force equals mv squared over L. Okay. Now, that's the force of just one particle hitting the wall. But of course, in this gas, we have many, many particles. Yeah? So this is just the force for one atom, or particle, or molecule, or whatever. So the total force would be m over L, V1 squared plus V2 squared plus V3 squared, etc. for all the particles. And let's say we have n particles, like this.
What does V1, V2, V3 mean? Different?
They're all different speeds of each particle, yeah, because some particles go fast, some will go slow. So we add them all up. Oh, and of course I'm assuming it's the same mass for each particle, that's the same gas, like hydrogen gas or something. Okay. Okay. Now what's the formula for pressure? Force over area. Okay. So that would be here, if I was to use this, m over L, V1 squared plus V2 squared, etc., all the way to Vn squared, all over, and the area here for the surface it hits is just L squared. Yeah. So I can clean this up a bit. I can say pressure is m over L cubed, and then we add all the velocities together. Yeah? Okay, good. Now you can kind of see what's going to happen here, because what's L cubed equal to, do you think? L cubed?
Volume.
Volume, yeah. So we can change this into pressure equals the mass of each particle over the volume, and these are velocities, be careful, V1 plus V2 squared plus all the way up to Vn squared. Now, it's a bit silly to add all these velocities together, because some will be fast, some will be slow. But if I just took an average, I can get a very, very, very good estimation here. So rather than looking at all the velocities, I'll just say P, pressure, is mass over volume, N multiply the average velocity. This means average. Sorry, and what I'm doing here is I'll put an n here and an n here. So now this here is an average. So I can simplify it even more. Sorry, I have to do that again. Tanish, you look very confused. I'll do this again. Watch. I'll put an n here and an n here. When I add something up and divide by n, that's the average. So this will be n times the average velocity squared of the particles, their average speed squared.
But why would you add n down there?
Well, I need to get the n down here to make it an average. To keep it balanced, I have to put an n above and below. I can't just put in an n because I want to. You know? Okay, so write that down. Yes. Yes? No, we can move to the next part? Okay. Now, we have to have a look at this piece here, because this is not quite as simple as it looks. If I go back here, in my example in the diagram of my molecule, I did my molecule going perfectly perpendicular into the wall. Yes? But of course, that's not going to happen. You'll have your molecules going off at different angles. So what we need to do is imagine our molecule is moving at some angle. It will have x component, Vx. It will have, of course, a y component, Vy. I know this isn't very clear. And it'll have a z component, Vz. And this speed here is v. We know from Pythagoras that v squared equals Vx squared plus Vy squared plus Vz squared. But if the gas is moving in all different directions, on average, these three numbers should be the same. Now think about that. If you had your atoms, and if most of the time the Vz was the biggest number in the atom, then what the atoms want to do? They want to move up the room. Okay? If most of the time the Vx was the biggest part, it would mean that the gas is moving this way. But if the gas is staying in the container, not moving left, right, up, down, it means on average, the Vx, Vy, and Vz should be the same number, on average. Okay, so we can then replace this with V squared equals Vx squared plus Vy squared, Vx squared plus Vx squared. They're all roughly the same number. So you get v squared equals 3vx squared. So you get 1 over 3 v squared equals vx squared.
So,
The point of this here,
the diagram, like the line.
no real point, I just like diagrams. Yes.
I'm using Pythagoras for the...
Pythagoras, yeah.
Isn't that be two?
Oh, Pythagoras, multi-dimensional. Yep. Can do 3, 4, 5, whatever. In many dimensions as you like. Can I go back to the main part?
Yes.
Yeah. So this v here really was always vx, because in my picture, when I did my calculation of the momentum, I had the particle perpendicularly hitting the wall. So it was really vx all along. So if I use this result I have here, I can replace it with P equals 1 over 3 mn over volume, velocity, this is a small v, squared. So I get this. Okay, so we're nearly finished there.
Why don't you put X in there? Why don't you put X in the formula?
Why did I put X?
Yeah.
Because what I was saying is, remember when we did our calculation of the momentum, I said mv minus mu? I assumed in my calculation that it perpendicularly hit the wall to make it an easy calculation. So all this time, I was only looking at Vx's hitting the wall. But in reality, the gas is moving in many different directions. So the result is, I basically have to divide by this 3. That it's not as big as I originally did it as. Yeah? Okay. So going on. Okay, so I want to make sure I get this last piece with the constants right. No, that's actually, yeah, so if I just rearrange this a bit, pressure multiply volume equals 1/3 n v squared. Now, think back to the ideal gas law I just showed you earlier. What is pressure multiplied volume? N or T. N or T equals 1/3 n v squared. We're getting there. That's what we're getting to. Cancel ends. So I get, and what I'm going to do now is I'm going to drop, what I'm going to do is multiply both sides by a half. So now I have a half or T equals 1/3 a half mv squared. What's a half mv squared? Yeah, so now I have a half or T equals 1/3, and then this is the average kinetic energy per atom, per molecule, per whatever it is you're looking at, per part.
We just need the temperature.
So yeah, if I just bring the 3 up here, you have 3 over 2 or T equals the average kinetic energy. There we go. That was the result I was trying to get to here. Now, if you drop this constant, you get this result. That temperature is proportional to kinetic energy average. This is not in the formula book. So after all that, the reason I wanted to show you this proof is that it's very simple ideas at the start. We had Boyle's law, Charles's law, and then the pressure volume law. We put the three together and made the ideal gas law. Remember that? And then I just used what we learned from semester 1 with mechanics. Hey, why are you so late? I don't know, why are you so late? Huh? It's noon. How do you oversleep for noon? Sit down. So we use that and what we've learned from mechanics, and we have this really useful result. We now know what temperature means. Look. Try to impress you here. We now know what temperature means. Temperature tells us how much kinetic energy there is per particle. So this is what happens. When you increase the temperature, it means you get more kinetic energy per particle. They move faster. Okay? So please make note of that. And we'll have to put this as a statement at the end. So this means temperature is a measure of how much kinetic energy each molecule has. And in fact, temperature, we can say it is 2/3 or multiplied by the average kinetic energy. What would happen if the temperature equals 0 Kelvin? What does that mean? Yeah, that means that the average kinetic energy is 0, which means the average velocity squared is 0, which means no movement. So at 0 degrees Kelvin, the molecules are locked into place. There's no movement with them. They're completely stationary. For anything at 0 Kelvin. I know this proof, I used a gas, but in fact it works pretty well for solids and liquids. But it's still true for anything at 0 Kelvin. There's no motion in the molecules. They're completely stationary.
Is that possible?
Yes. Oh, yes. It's very difficult to get things at 0 Kelvin, but there have been things put nearly at 0 Kelvin, like 1 Kelvin maybe, half a Kelvin.
Is it because to create a machine that will make it 0 Kelvin, while the machine will work and it will stop? Because it will be 0 Kelvin inside of it.
Yeah, but the problem is it's very difficult to have something isolated and to take all the heat energy out of it without accidentally putting some heat energy back into it. It's really difficult. In fact, even if you were in the middle of space, you couldn't be at 0 Kelvin. Because actually space, does anyone know the temperature of space? It's cold, but it's not 0. Does anyone know? No, temperature of space is 2.7 Kelvin. So even if you were in the middle of space with no star, no planet, no ship, you still would not be at 0 Kelvin. You'd still be at 2.7 Kelvin. Yeah, some 2.7 something. I thought it was 2.71.
Is that the reason the movement is very slow?
In what situation?
In space, right? Movement is slow.
No, it could be fast. All I'm saying here is, even when you think you're in no heat near you, that you're in the middle of space with nothing around you, space still is a little bit warm. 2.7 Kelvin is the temperature in space. Huh? You can't, there's nothing zero. So if you want something zero, no, not even that. If you want something zero, you're going to need to build a special room that's completely cut off from everything else. Very difficult task to do. Because even here, 2.7 Kelvin for space. Okay. And why 2.7? Does anyone know why it's not zero? No?
Stars.
No, there are no stars around. In the middle of space, away from everything.
Why?
So the reason is it's leftover radiation from the Big Bang, keeping everything still a little bit warm. Still, everything's still cooling down. Okay, so this is why it's 2.7, but it's decreasing in time. So give it another few 100 billion years, and it'll be less, if you wait that long. Okay, now, of course, in the exam, they won't ask you for this proof, but they could ask you something like, explain what is causing the pressure here. So what is causing the pressure here? Well, the pressure is caused by the force. The force of what? The force of the atom changing its momentum when it hits the wall. You know, this is what I mean. The proof is not on the exam, but they might ask you something that tests your knowledge about this proof. Okay? So they could say something like about the pressure, or they could say something like what is meant by, or what does temperature measure? Now, if I asked you before today, what does temperature measure, what would you say? No, before today you would have said that?
Degree of Celsius.
So look, this is where we have to be very clear that heat is an energy in joules, and temperature measures, as you said, Joshua, degree of hotness. But what the heck does that mean? Well, that is just a measure of kinetic energy on average for each atom, each molecule.
Is that the only thing?
It's all that I've seen, yeah. I'm not sure. I will have to look at past exams, but I think all the examples I can think of is just this one. Yeah. Okay. Let me just check something here. Okay, maybe we'll do a little example. Possibly. No, I don't think so. I think there's enough said about that. Okay. Can I continue on? Yes? Okay. Alright, so we did this first part is what's called, go back to the stop here. What we've just looked at is what's called the kinetic theory. Now we're going to look at thermodynamics next, just a little bit. Okay. So just some definitions first. Thermal equilibrium. If A and B are in thermal equilibrium, that means they're basically the same temperature. they're the same temperature, I'll just say. Same temperature. Or in other words, no heat exchange will take place. Well, no net heat exchange. Net. Write the word net in there. No net heat exchange will take place. So, if you think about this as an example with your cup of tea, the tea starts off really hot, but if you leave your tea long enough, then the temperature here of the tea will be the same as the temperature of the air. And then when that happens, we say they are in thermal equilibrium, that no more heat will transfer between the tea and the air, that they are now the same temperature. So this is thermal equilibrium. Okay. Right, so we have 3 laws of thermodynamics. And I should explain what thermodynamics means. Alright, so what does thermo mean? Temperature. And what does dynamics mean? Movement, change, or equations, if you want to think about it like that. And thermo means temperature. So in other words, we're going to write down some formulas about temperature, how it behaves. So the first law is called law 0. Yes, 0. If A and B are in thermal equilibrium, and B and C are in thermal equilibrium, then that means, therefore, A and C are in thermal equilibrium. So this isn't, it seems very obvious, doesn't it, that if A and B are in equilibrium and B and C are in equilibrium, there's no temperature change. Therefore, if I put A and C together, they too are in thermal equilibrium. So it seems pretty obvious, doesn't it? That's called the 0 law. No, it's more just a statement about thermal equilibrium than a formula. Yeah.
Thermal equilibrium, same temperature.
Yeah. So it would mean like if my pen and the table were the same temperature, and if my pen and this table were the same temperature, then it means that these 2 tables must be the same temperature. Pretty obvious, right? Okay, the next law. Do you have this? Yeah? Okay. So now the second law, which is called law 1. So the second law, which is called the first law, okay, because we start counting at 0. Okay, so I just need to explain some terms here. Okay, sorry. Can I go to the side? Yeah. So just to give you some terms here, you have some system here. Could be anything, a car, truck, whatever. And this system here, it does some work. So there's some work energy coming out. So for example, if it's a car, it has kinetic energy. That's the work it's doing. Okay? If it is a television that is sending you light and sound. So this is called, this symbol here is the work done, but you know this from semester 1. Now we put some energy into it. This energy we put into it, we'll call this letter Q. And the reason it's Q is because usually it's heat, but it could actually be any energy that goes into it. Okay. Now let's not forget, remember inside I said that we think of this as lots of little particles. And what happens if the temperature increases? What happens to the kinetic energy? Increases. So if I put heat into this, maybe these particles will get hotter, they move faster. So they could change their kinetic energy, or as we say, they could change their internal energy, meaning they could get more kinetic energy usually. So this one is called internal energy. So let me give you a very simple example that maybe you can think of at home. So if you have your laptop plugged in, and let's say there's energy going into it, like this. What energy do you get out of it? What form is it? Light and sound. So you get energy coming out. But doesn't your laptop get hotter?
Yeah.
So it gains internal energy. We know that energy is conserved. So we know that the energy that goes into it equals the energy that comes out plus any energy it gets inside of it, which could be like heat. What would happen if your laptop was broken, but it was still getting the same energy here? What does that mean for this? Is it more or less?
More.
It's more. Because this must stay balanced. So your laptop will just get hotter. This here is actually the first law, conservation of energy. The energy you put in must equal the heat or internal energy plus the work done. That's called the first law. What goes in equals the internal plus the work. So write that down. That's the first law.
That is with S, right?
Huh? No, sorry, I didn't say. That's a delta, means change. Hang on. This will make you feel better. Delta Q equals delta U plus delta W. All better? Now I should point out, because we're talking about thermodynamics, this here will represent heat. Okay? So I know in my example I used the laptop with the electricity, but for thermodynamics I'm only going to be talking about heat here. Okay? Can we think, yeah.
How do you put that in words, the first one?
Oh, we're just saying that the heat energy provided to a system equals the work the system does. Will I write down? Yeah. The heat energy put into a system equals the work done by the system plus the gain in internal energy, which basically means the machine gets hotter. The temperature raises in the machine. Okay, can I go down? Yeah. I'll give you a very, very simple example of what I mean by heat going into a system, which you can kind of picture, maybe something like a train. Hey, go ahead. Yeah. So if we think about like a train has a heat, and then what happens is it heats the water, and then the water changes into steam, and then the steam makes the wheel turn around, makes the train go forward. What I'm saying here is the heat energy here will equal the work done plus the increased internal energy. In other words, the energy that you put into this water to make it hot. Now, if you think about it, if you're putting heat into it, which do you really care about getting more, the work or the internal energy? The work. In fact, that internal energy is wasted because you don't care about making the train hot, you just want the train to go forward, an example. And the bad news is the third law, which is called the second law, says that delta U is never zero. That's the final law here, that the internal energy change is never zero. It can be reduced, of course, but we can never make it zero.
What about heaters?
Heaters?
Yeah, you plug it in.
But now remember, I said we're talking about systems where you put heat energy in. So heaters take it, yes, electrical, yes. So whenever you put heat in, you can never avoid causing an increase in internal energy. It always happens. And this is the reason why we have efficiency less than 100% always. This is another way to say the second law, that efficiency must be less than 100%. Yeah, you got that? So actually, I'll go back to, well, no, just, what's that?
Does this apply to the friction in machines?
Yeah, because friction is increasing internal energy. And, please, this law, how it was proven, I can't remember who proved it actually, but this is how you could prove the law. What he did was, he had a barrel of water here, and in the water were these paddles, and up the top here came out here, and it was connected to a wheel, connected to a weight. So what you have here is, what type of energy does this weight have at the start? It has potential energy. When this falls, this potential energy gets changed into turning this, which is kinetic energy. But then this kinetic energy gets changed into making this hotter. The water gets hotter because it's spinning. So in fact here the potential energy makes the water hotter. So the potential energy actually gets turned into heat. Okay? But of course, it's never going to be perfect. Some energy will be lost, some will be wasted. For example, here, maybe some heat escapes or something. Or maybe here some sound escapes. But anyway, what I'm showing you here again is just conservation of energy. Now what's interesting is, could you do the opposite? If I make this hot, could I then make the box go back up? What do you think? You could, yeah. So for example here's a lot of water, and then here's some heat here. But when you heat up the water, it starts to move this way around. If I put the heat down the end here. the water starts to move around. This is what happens in the house with the heaters here. You know, when you heat the water up, the water will start to move around the house. Okay? This is why the heater is always on the ground floor in a building, because the water will move around the house like this. So you can imagine, okay, so if I put a little wheel here, what will happen to this wheel? It will start to turn. And maybe this here could lift then our box up. So this is the work that's being done. It's the potential energy. And this is the heat that's being provided. Sorry, you don't like this symbol. This is the work that's being done. It's potential energy. And this is the heat that's being provided. So we know that the heat provided will equal the work done plus the internal energy. What's that going to be here, the internal energy? No, not the movement, because not quite the movement of water, because we kind of want the water to move to raise the block.
The heat energy of the container.
Yeah, almost. It's the temperature of the water. So what's happening is, when the heat goes in, it warms the water, which causes the water to turn. This lifts the box. But also what happens to the water, it gets hotter. And you don't want it to get hotter. What you really, really want is all your heat to somehow just make the water turn, but not get warmer. Is that possible? No, it's not possible. So again, this is me saying the second law, that it's impossible to make this zero. But the nearer to zero you make it, the better. Okay?
It's the same idea in dams.
Not for dams actually. Really, this type of stuff we're talking about is, no, that's for turbines. No, that's something which we'll do in the next part when we do fields. What this stuff is really important for is anybody who's going into engineering, mechanical engineering, aeronautical engines. Anybody doing that? Yeah, what did you do? Mechanical or?
Civil and mechanical.
Civil and mechanical. Okay. What are you doing? Yes. Oh yes, about that. Anyone mechanical or engineering or? Mechanical engineering or aeronautical, automobiles, anything like this? No. So this type of stuff is really important for engines. You think about like a car engine. What happens with the petrol? It causes a flame. The flame heats the gas in the chamber, and the chamber expands. Then when the chamber expands, what happens to the wheel? It gets pushed around.
So why do cars need water?
To keep them cool, or they'll just explode. So the water isn't for steam or anything. It is really just to keep it cool. So let's see. Yeah. So next, since we're talking about cars now, we'll look at the piston. Okay. Right. Can I go down? Yep. Okay, so you remember I said with the car, you could have something like this. I know I'm not drawing it nicely, but you get the idea. That if this gas in here gets bigger and smaller, this piece here will move up and down. If this moves up and down, then this turns around. If this turns around, it makes your car go forward. So this is the work that's being done. So my question then is there a formula to calculate how much work is being done when the gas is changing its volume? In other words, if you change the volume of a gas, you can do some work, because you can push something, turn something. Okay, so let's have a look. What is our basic definition of work from semester 1? It's force times distance. So we'll call the distance that it moves delta x here. But recently, what is our formula for force? Pressure over area times delta x. Force is pressure by area, isn't it? Pressure is force over area, so force is pressure multiply area. Yeah. But what is area multiplied distance? Like here, if I have area and I multiply it by this distance, I get the volume. But just be very careful about what I'm saying the volume is. I'm not saying this volume. Look carefully here. Here's my gas here, and then it increases to here. So this piece here on the bottom, that's the area. If I multiply this area by this height, I get a volume. But it's not the volume here I got, it's the extra volume I got. In other words, it's the change in the volume. So back here, I can replace this with pressure multiplied the change in the volume. Okay. Now this formula only really works if pressure is constant, which it's not, because the reason it expands is because you increase the pressure and so on. But still, it gives you a good approximation. You can say that the work done by a gas is approximately the pressure of the gas multiplied the change in the volume of the gas.
Is that the formula?
And that's the formula, yeah.
Does this only work for piston or anything?
No, that works pretty much for any gas that's changing its volume. It could do some work. But interestingly, the opposite is true. So if you then shrink your gas, then you have to do work. You have to put energy into it. So to compress your gas requires work. How much work? Well, you can work it out there. It's the pressure of the gas multiplied how much volume you decrease it. Now again, I remind you why it's only approximately true, because what happens when you reduce the volume? What happens to the pressure? It increases, doesn't it? So that's what I mean, it's only roughly true. It's not exact, approximately.
Because what if we will increase the volume and decrease the temperature?
Yeah, and then there's also a problem with temperature change as well. The temperature is constant here too. So pretty much, if you manage to keep pressure and temperature constant, but reduce the volume, then it'll be exact, which won't happen.
Is this similar to expansivity? Like volume expansivity?
Yeah, it is, yeah. Not directly, we don't deal with that so much in it. There's some connection. Okay, so what I want to do now is talk just a little bit more about moles. I just had it at the start very briefly because I wanted to have the word introduced for the ideal gas law, but we'll just look a little bit more at mole examples here. Okay. Sorry, do you have this? Yeah? Okay, so we take something like H2O. What's this called, H2O? Yes, but just in general, when you have molecule. Okay, so please just be careful with the words here. We have a molecule. Okay, and then of course we have this by itself, they're the atoms. So if I have 1 mole of H2O, how many hydrogens do I have? I have 2L of hydrogen. And how many oxygens would I have?
1.
I'd have 1L of oxygens. So just be careful here with molecule and atom, okay? Yeah. Okay. I'd like to know. I'll give you a small example to try and help you remember your calculations for mole and molecule and so on. I say I have 1 kilogram of water. I would like everybody here to calculate how many hydrogen atoms I have. So if I say I have a kilogram of water, tell me how many hydrogen atoms I have. That's what I want you to do for me. You don't need the periodic table. You should know the numbers. Hydrogen is 1, atomic mass is 1, oxygen is 16. Isn't it? So I want to know how many hydrogen atoms do I have? Atoms, yes. Well, let's have a look at it now. So, first thing I need to do is I need to know how many moles I have. So I have 1 kilogram of H2O. That means I have 1,000 grams of H2O. What is the molar mass, or what is the molar mass, isn't it? Yeah, molar mass. What is H2O? Well, it'd be 1 plus 1 plus 16. So it's 18 in total. So what that's saying is 1 mole of H2O equals 18 grams. So if I do 1,000 grams divided by 18 grams, that should give me how many moles of H2O I have.
65.5, which is 500 over 9.
500 over 9. 500 over 9 moles of H2O. What is that number?
55.5.
Thank you. 55.56 moles of H2O. Okay, so we're nearly there. So that means I would have 55.56 times Avogadro number of H2O. But in H2O, I have 2 hydrogen atoms and 1 oxygen atom. So that means I would have, two times 55.56 times L of hydrogen. What number is that, please?
6.68, 6.69 times 10 power 25.
6.69 times 10 to the power of 25. That's how many hydrogen atoms I have. So this is really the usefulness of moles and the periodic table. If you think about it, what you've just done is, I said to you, you have 1 kilogram of water, and you're able to tell me how many hydrogen atoms I have. So this is why moles and the periodic table are so useful. We can do things like this. And this is important. And the reason that this is important is because in my formula I gave you at the start, for PV equals N or T, the N, you need to know what that is. So you need to be able to work with moles and atoms. So what might happen in the exam, for example, is in the exam they could give you like how many atoms you have, and you have to work backwards to get the moles, because in this formula here, you need to use moles. Okay? But there are other ways to write this formula. So you might know from chemistry as well, if you have N moles, then how many of that thing do you have? Well, of course, it is N multiplied L. Yeah? Like the amount, yeah. So some people don't like to have the N in here for moles. they much prefer just to have the amount, not the moles. So you could write this formula as PV equals N over L or T, or you could write it as PV equals N or over LT. Now I think, Tom, you were saying earlier about Boltzmann's constant. I'm not 100% sure, I'll need to check my formula book, or actually the calculator here. But can you type this in on your calculator? It will be another constant which I'm going to call K, and I think this is also on your calculator. So if you just do 8.31 divided by Avogadro, what do you get? 1.38. 10 to the minus 23, yeah? Okay, can I have the Casio calculator with the lid? How do you get the constants of shift 7? It's on the calculator. Yes. So Tom, the Boltzmann constant represented by the letter K is just the ideal gas law constant divided by Avogadro's constant. This is actually on your calculator as well, it comes in 25.
What is this?
It's just the number, the amount. So whatever. So like in my example with the students, 1 mole of student, the small n is 1, and the big N will be 6 times 10 to the 23. The big N is just a regular count, and the small n is how many moles count.
What are we going to use those for?
This is all theory. It's all theory, and then the next class we'll have a look at exam questions. But the syllabus has this listed as something the students need to see, and for the exam, really, if this came up in the exam today, it's double lesson. It's not a calculation question in the exam, it's an explanation question. So the question in the exam could be, for example, what is the difference between solid, liquid and gases at the molecule level? It could say, what does it mean to be at 0 Kelvin? It means no kinetic energy, everything is stationary. You know, it could say, I think one year I saw something like, what is the unit for pressure multiplied volume? So what's the unit for pressure? It's newtons per meter cube. And you multiply by meter cube, what are you left with? Newton, which is work. So basically it's like my example with the piston. They said, show that the units for pressure multiplied volume is force, work, joules, isn't it? I can't even remember what I'm saying now. It's force. Lost track of what I was saying. Anyway, for the exam, all of this is just conceptual questions, you know. What else can we look at? We have ideal gas law. Now, ideal gas law, we'll do that questions. Next class is tomorrow?
Yes.
1 hour. Next week. Okay, good. Yes. Yeah. And also, yes, another thing they could ask in the exam is they could say in the exam, explain why it is not possible to be 100% efficient. So what's the reason? The second law, thermodynamics, that when energy goes into a system, the internal energy must increase, therefore the work will be reduced. So it's all just conceptual questions here. The next class will go back to looking at problem solving. Yes? At these? What? I'm going to get my lunch, I'm hungry. Alright, we'll finish there.